Hi, so we're going to talk about our big data project. This involved implementing machine learning algorithms in MapReduce and also providing real-time visualizations for those implementations. So our primary motivation for doing this project was through our experiences using existing libraries like Mahout. These have very good performance, but they don't provide any really nice visualizations of the actual model that's being run. So really, they only say how far the mapper has progressed or how far the reducer has progressed. And what we really wanted to add to this was some algorithm-specific visualization. So in our case, since we're doing neural networks, we want to visualize the training error of the neural network while it's being backpropagated, while it's being trained. And the advantage of this is that you can decide to kill a job early on when you realize that, oh, it's like, say you made some mistake in the initialization and the error isn't what you expect, or the model convergence isn't what you expect. And so that could potentially save a lot of time as you're waiting for these models to run in like 10 minutes or 30 minutes or anything. So really, our goals for this project were to, first of all, implement a neural network algorithm in MapReduce. Is proved to be an interesting challenge to try to parallelize this algorithm. And secondly, during the execution of the training process, we wanted to also provide some real-time visualizations so that when you're running this, you really have a better idea of what's going on internally, in this job. And lastly, the tools that we used were primarily Java for the MapReduce implementation, and also Python, Flask, and other resources for providing the web server and the visualization on that web server. So the way the neural network works is, well, first of all, we decide to implement a three-layer, the traditional three-layer backpropagation network. And when you pass data into a neural network, first it gets passed into here, these input layers, and each of these, the output from this layer gets scaled by these weights, and then these also the outputs from the hidden layer gets scaled by a different set of weights going to the output. And for each set of nodes that receives input from the layer before it, it, um, it combines a sum of all these weights multiplied by the inputs, and then passes that sum through a sigmoid activation function, and that determines what the output is. And in terms of the training process, you are trying to, first of all, it's like a gradient descent algorithm, and the goal is to minimize the sum of squared error between the vector of outputs here and the true class of your training data. And the way it does it is through this set of equations. So this is really saying um, the error is determined by the difference between the output and the true class, and that's scaled by the derivative of the sigmoid function of the output. And this really just becomes the output times 1 minus the output. And it's a similar process here with the scaling, retraining the hidden weights, only in this case it's not directly the difference in the output, it's the set of output differences here scaled by the weights of the hidden nodes going to each of those outputs. And that determines the weight updates here. And that every iteration you pass a subset of data or maybe a single data point through, and these weights are applied. And you do this over many iterations or epochs. So the way we decided to design this neural network for a MapReduce application was that we really couldn't split up kind of the internal, backpropagation process here. So what we ended up doing was something similar to the way a random forest works, in that we decided to train several neural networks of the same kind of overall architecture independently, each receiving a random subset of data from the HDFS. And so a different set of data goes into each of these map functions, and then within each map function, there are independently n iterations of the forward and then back propagation process. So each of these gets trained independently. Now, after they get trained, the complete network consisting of all the weights and basically the weights and kind of their position within the network, our output, to the reducer. And so for our final model, we decided not to average it. We decided to basically evaluate each of these models on some data and then output the model that had the best training error. So the performance of these models depends not only on the subset that was input into them, but also in the weight initializations. And the combination of these creates networks that are kind of trained differently according to the training set. So we tend to pick the model that has the best performance out of all these. So the input data that we decided to use was the MNIST set of handwritten digits. These are grayscale images that consist of 28 by 28 pixels, and this gets read into our first as an input file of 784 basically comma separated flow values. And the total data set comprises 60,000 training examples, 10,000 test examples. We ended up using a subset from 0 to 3 just for presentation purposes. Now, in terms of the visualization, you can see that the MapReduce job is running right here. And this is our visualization that we have running on web server. So what this shows here is the full set of mappers, each receiving their own set of inputs. And this is the iteration number of that mapper. So for example, in this mapper, it receives a set of data at 100 iterations. And initially, since the random was randomized, it produces a very high error for the training function. But as you propagate, this error very steadily goes to 0. And then at 200 iterations, you see that it received another set of inputs, and then it continues the process all over again. And then occasionally you see here that the mapper doesn't converge to 0, it has some non-zero error continuously. And this is really either a product of the initialization or a product of the particular set of data that was passed in. And the good thing about this is that as your job is running, this gets updated in real time. So what you see is as this progresses, then this plot grows. And this is when the job finishes. This is what you see is for each mapper kind of the set of data that got passed in, and then the training process. So in terms of the classification results, this is initially we had some issues with this, and that was because we were averaging the models together in the reducers. So we switched to simply picking the best model based on some validation set. And we ended up achieving much better results. And we think the reason for this was because all these independently trained neural networks were converging to different local minima. So averaging them ended up pulling them out of those minima and then into some suboptimal configuration. So we ended up just picking a single model, and overall that's tended to work very well for us. We got an accuracy of 91.3%, which considering we didn't perform any pre-processing on the data, we just inputted the vector of pixels directly into the model. We consider this to be quite good. In terms of improvements to accuracy, oh yeah, I just talked about that. So in terms of potential for further improvement, we could consider doing some pre-processing on the data. For example, we don't account for things like translational or like rotational error, things like that. So that's if the digit is shifted to right or left, then a different set of pixels gets activated. But in general, we're quite happy with this performance. Okay, in terms of future work, we had originally planned to do some graph visualizations of the structure of the neural network. We actually got this working in D3, but what we realized very quickly was that it's a little infeasible to visualize all 780 or so inputs and then 400 hidden nodes. And the implementation itself was quite slow in D3, so we ended up leaving this out for now. We're not sure if we'll put it back in. Maybe there's a useful way to visualize a subset of the data or something like that. In terms of we could choose to improve the neural network by pre-processing, and we decided in the end not to finish implementation of the random forest. So overall, that's our project. Thank you for your time. Hi, so we'd like to just quickly demonstrate our MapReduce implementation in action. So first, what you need to do is start the visualization. So then you can connect through here. And so right now there's no output, but then we run the job. And notice that this is being run on a different library than our input. So we had to run a separate job to scramble the input data. And instructions for doing that are in the README. And so what you can see is that for a single mapper, as the training process progresses, the error on the subset of data that was input to it, it decreases. And these spikes are when each of the mappers receives a new set of data. And so that restarts the training process.